All right. Just 1 second. I guess a pointer would be nice. There we go. Okay. So yes, I would like to join everyone in thanking Lev and Avi for organizing this nice meeting and letting me present our work here. And also congratulations on inaugurating Quest, and best of luck in your future. What I'd like to tell you about today is the implementation and our plans of using engineered subspaces for the purpose of precision spectroscopy. Better? Okay. Using trapped ions at the Weizmann Institute. This work was not done by me, but rather by a hardworking group of graduate students whose names show up here, but nevertheless, I'm going to tell you about it. So the idea is the following. We often use quantum systems to perform seemingly two contradicting tasks. One is that of getting information. We use quantum systems as measurement probes. And what we need out of measurement probes is for them to couple to the environment as best as we can to collect information from the environment. We also use quantum systems often in order to carry information and store information or transfer information. In this case, the physical requirements are seemingly, at least, completely opposite. We like these quantum systems to decouple from the environment as much as we can. So at face value, you wouldn't use the same system or the same strategy to perform the different tasks. But as in many seemingly contradicting concepts, there's a lot of common ground. And in this case, noise is a common enemy. And in the context of quantum information processing and quantum information storage, many techniques have been developed in order to protect our systems from noise. And one can take these techniques, these methods, and then use the long coherence times that you get in order to measure things very precisely. And in the trapped ion community, people have been using these strategies quite a lot. This is a list of recent examples from the last 10 years or so. People have been using these engineered subspaces, decoherence-free subspaces, in order to measure atomic quantities, such as quadrupole moments in trapped ions. People have been using these subspaces to measure Lorentz invariance. Decoherence-free subspace is not the only strategy that people have used to this end. People often use dynamic decoupling, so the fast modulation of a quantum system that spectrally separates it from the environment. If you like, the fast modulation dresses the system up and opens a gap between the two dress states of the system. And this gap prevents from the environment to couple these two systems. And it has become very common to use these techniques in order to measure things precisely. In our group, we used it in order to perform precision magnetometry. We've used it in order to measure, again, an atomic quadrupole moment in a single trapped ion. We use it in order to measure forces very accurately. This is just a list of examples coming from the trapped ion community. There have been many experiments in other experimental platforms, such as NV centers, superconducting qubits, neutral atoms, and more. Now, because Quest is a quantum entanglement science and technology center, I chose to focus here on two experiments and one proposal in our group where we used entangled subspaces in order to perform precision measurements. The first experiment I'd like to talk about is the way we used an entangled subspace in order to perform Heisenberg limited Rabi spectroscopy on a 2-ion crystal. I want to describe an experiment where we measured the magnetic interaction between electrons using such a subspace, and I also want to describe a proposal in which we would like to use an entangled subspace in order to reject systematic shifts in atomic clocks. The platform we use is that of trapped ions. This is a picture of one of the traps we use. Here you can see 3 trapped ions, a Wigner crystal and 3 trapped ions. They're cooled to temperatures well below 1 millikelvin, so they freeze into these nice Wigner crystals. The trap harmonic frequencies are in the megahertz range, so these are pretty stiff traps, and they hold the ions tightly. The ions we use are strontium plus ions. These are alkaline-like ions. They're very similar to rubidium. The ground state is a zero angular momentum state with two spin 1/2 electronic spin states. There's no nuclear spin to strontium-88, so there's no hyperfine structure. The two other excited states which are relevant for our purposes is a strong dipole transition to the P1/2. This is a very short-lived state. The coupling is very strong. We use this in order to perform Doppler cooling. We use this in order to perform state-selective fluorescence, so it's a very useful transition for us. The other transition we use is a very narrow electric quadrupole transition. This is an optical clock transition. The lifetime of the excited state is very long. It's 0.4 seconds. There are 6 Zeeman states to this manifold, and we use a narrow line with red laser in order to work on this transition. There is actually, where is Adi? There's a hidden link. I'm guessing when you saw my title, you thought there's nothing in common between what I'm going to speak about and what Adi spoke about. There's actually one connection, I guess, which is Anna Kesselman, the student who was, for her master thesis, built this laser, was so traumatized that she went on to do her PhD with Adi, working on non-abelian excitations in wires. So these are narrow line with transition. We can scan the laser. I'm sorry. No mercy at the Weizmann Institute. So you can scan the laser frequency across this transition. You can see a nice carrier resonance and motional sidebands that are due to the periodic Doppler shift of an oscillating ion in the channel. And this laser in transition is a major tool in our experiments. We use it in order to engineer, or build, if you like, our entangled subspaces. And we use it in different modes of operation. One mode of operation is that of global rotations on these superpositions of S and D states. We can either address an ion register, an ion crystal, with a global beam and perform Rabi nutation on all these ions together. So you can see nice Rabi nutation or a nice spectroscopy of these 3 ions in parallel. Or we can focus the ion tightly onto single ions in the register, and this way perform Rabi nutations on an ion of choice. Okay, so we can perform rotations on these superpositions, either going ion by ion or together globally on the register. I already made a connection to one talk in this session, connection to another talk this afternoon is the speaker of the first talk this afternoon. Before he was thinking on how to generate entangled states using dissipation, was also thinking hard about how to use unitary operations on trapped ions and creating entangled states. So the Malmer-Sorensen gate is the gate we rely heavily on. We use the optical transition from S to D with a bichromatic light field, which is off resonance from the singly excited manifold. And by doing that, if we detune our lasers far enough from this single excitation, from the motional sidebands of this single excitation, we can initially excite motion in this 2-ion crystal, but after a time which equals 1 over this detuning from the motional sideband, motion goes to 0 and direct coupling, if you like, from SS to DD is formed. What you see here is the population of the ions in the SS. So to begin with, it's 100%. And after the gate time, it goes to 50%. And the population in the DD state also goes to 50%. And we have a superposition of the ions being in the SS and the DD state. And to verify that this is indeed a coherent superposition and not a mixed state, we rotate this superposition and look at interference fringes between different states, and we can see that the parity, meaning whether the number of excited ions is even or odd, oscillates as the function of the rotation phase. So this is indeed a coherent superposition. By the contrast of this, by the contrast of this fringe, we can extract the fidelity with which we generate these entangled states, and it is relatively high. Now, in order for this fidelity to be high, you need everything here to work properly, so the gate parameters have to be well tuned and so on. In particular, you need that the sum of 2 frequencies here would match the SS to DD transition. And now I'm going to show you a transparency. It's not, I have to apologize. Unfortunately, it's not very visible here. This is a transparency, which is a side note, so this entire transparency is in parentheses. It's not directly related to the topic of the talk, but I couldn't resist because this paper came out on the archive today. In order to reject noises in these gates, we wanted to apply dynamic decoupling. The problem with dynamic decoupling that is used during such entanglement gates that couple motion and spin is that the dynamic decoupling pulse would also reverse the direction of the force, and that would mess up the gate. And Alex Retzker, with whom we collaborated, came up with this smart idea of if you time the gates right and you choose the phase of your dynamic decoupling right, you can reverse the direction of the force, but you can still perform closed motion in phase space. And rather than performing circles in phase space, such as an off-resonant force would do, you create these nice flowers, and the number of petals here equals the number of dynamic decoupling pulses you implemented, and we implemented this protocol, and you can't see it here very clearly, but it does mitigate detuning noise. Anyways, I know this was fast, but it's not part of the talk, so it was more of an advertisement. All right, so we wanted to do precision spectroscopy. Let's try and zoom in on this optical quadrupole transition, and we can do that by reducing the laser power and getting narrower and narrower resonances. This is pretty much the narrowest resonance we're able to get. It's about 50 hertz wide, which corresponds to a Q factor of about 10 to the 14. This is by no means the state of the art of this industry. People have demonstrated Rabi line widths on these transitions, which is at least an order of magnitude smaller. This is data from the aluminum ion clock at NIST, at the Dave Wineland group. And when you look at these resonances, you can ask questions like, what's the resolution with which I can find this central frequency, which has to do with the line width, right? The size of this spectroscopic feature. You can also ask, what is the stability with which I can interrogate this resonance and find the center of this fringe with better growing precision. And you can also ask, how accurate is this peak, and whether it has all sorts of systematic shifts that would shift it away from the correct value. And I want to show you that by using entangled subspaces, we can address these questions, at least the resolution and line width question and the accuracy question, quite effectively. So the first experiment I want to describe is that of performing Heisenberg limited Rabi spectroscopy in a two-ion entangled subspace. So people have been suggesting and implementing protocols to use entangled state for the purpose of measuring spectroscopic signals with Heisenberg limited resolution. And the general method is a Ramsey spectroscopy type method. So in this example, one would prepare an entangled GHZ superposition where all the atoms are in a superposition of all of them being in the excited state and all of them being in the ground state with some phase. Now, the energy separation between these two states is n-fold larger than the separation than the frequency or the energy of your local oscillator. And therefore, when you scan the phase of your local oscillator, the phase of this superposition would oscillate n-fold faster. Okay, and what you see here is data taken by the Rainer Blatt group at Innsbruck with data going up all the way to 14 entangled ions. And you can see that indeed the phase oscillates n-fold faster, and therefore the slope here would be n-fold steeper, which means you can find the phase difference between your local oscillator and the superposition with an n-fold improvement, leading to Heisenberg limited spectroscopic resolution. And there have been other methods, all of them related to this approach. So for example, with many atom ensembles, people have demonstrated spin squeezed superpositions, which were not quite Heisenberg limited, but certainly for similar reasons performed with substandard quantum limit frequency resolution. Now, this whole approach is valid in terms of how precisely can you measure your frequency when you're working against projection noise, when your noise is quantum mechanical. When there are classical noises around, sometimes or most of the time, these methods would not buy you a huge factor. They might buy you, depending on details, a finite factor. And this is due to the reason that classical, so for the same reason that these superpositions are sensitive to your local oscillator phase, they will dephase faster as well. And you can see that as a demonstration here, the contrast of these fringes decreases as you go to larger and larger superpositions of entangled states. So we want to demonstrate Heisenberg-limited Rabi spectroscopy, not Heisenberg-limited Ramsey spectroscopy. So let's compare Ramsey versus Rabi spectroscopy. So in Ramsey spectroscopy, we prepare superpositions of the atom being an excited and ground state. And then we let them evolve under a free Hamiltonian. The free Hamiltonian would simply be a sigma z rotation with some detuning. And the detuning is the parameter we would like to evaluate. Okay? So we let it evolve for some time. It rotates under this sigma z rotation. We prepared on purpose a vector which is perpendicular to that sigma z rotation. It points in the x direction, for example. We measure the rotation angle and therefore estimate delta. When we perform Rabi spectroscopy, we take a different approach. In Rabi spectroscopy, we start out with an initial state which is in the ground state. But then we let it evolve under a Hamiltonian, which has some component of x rotation and then some component of z rotation that we would like to evaluate. Now, by measuring the amplitude that was transferred from spin up to spin down, we can evaluate the rotation of our Rabi vector, the angle with which our rotation vector points. And this is the way we estimate our detuning, this parameter that we would like to estimate. Now, what happens when we generalize to multi-spin entangled states? When we generalize to multi-spin entangled states, the state that we now generate is, if you like, a hyperspin state with a much larger angular momentum in each one of those arms. And the evolution now is, again, the evolution under a free evolution Hamiltonian. The frequency with which this state would evolve in this subspace would be n-fold larger under this Hamiltonian. Now, what shall we do if we would like to take this many-spin state and perform Rabi Heisenberg limited spectroscopy? So to do that, we would like to rotate this vector in this subspace, in this hyper-spin entangled subspace. And to do that, we need an entangling Hamiltonian. So for a two-spin register, if we would like to rotate the down-down state in the down-down-up-up subspace, we would like to use a transverse Ising Hamiltonian, an Ising Hamiltonian that collectively couples these two spins, and then the tuning, which we would like to measure. So in the last few years, and in particular in the trapped ion community, people have been busy trying to implement quantum simulation Hamiltonians to realize experimentally such transverse Ising Hamiltonians as well as other interacting spin Hamiltonians. So again, you can take the Malmer-Sorensen gate, and by detuning far enough from these motional sidebands of this singly excited states, you can adiabatically eliminate these states and look at this Hamiltonian as a Hamiltonian which directly couples SS to DD, giving rise to an Ising term here. Okay? Now, how do you generate a transverse magnetic field? You simply detune your two-photon resonance from your local oscillator, the average frequency of these of this bichromatic lever from this two-photon transition, leading to a collective detuning. So we can synthesize these transverse Ising Hamiltonians in our lab. So one way to think about what would these transverse Ising Hamiltonians do to two-ion subspaces can be understood by taking an algebraic approach. So we can write down our Hamiltonian as an Ising term plus a detuning on one ion and a detuning on two ion. These two can be equal, but they can also be different. In this case, I can write it as some average detuning on the two and a difference in the detuning of the two. Now, one thing to notice about this Hamiltonian is that this Hamiltonian commutes with Z1, Z2, or in other words, it conserves the parity of the excitation, which means I can now take my full Hilbert space and break it into two orthogonal subspaces, one which has even parity and one which has odd parity, and this Hamiltonian would not mix between these two subspaces. If I initialize myself here, I'm going to stay here. If I initialize myself here, I'm going to stay here. Now, if I'd like to implement rotations in these subspaces, it's easy to see that the Ising term here would look like an X rotation in both subspaces. But the Z rotation in the two different subspaces are different operators. The average, the tuning, would look like a Z rotation in the symmetric parity subspace. Okay, it would introduce a phase shift between SS and DD, but it would not do anything in the antisymmetric subspace. This is a decoherence-free subspace with respect to the average tuning. On the other hand, the difference between the tuning of the two ions would act like a Z rotation in this subspace. It would reduce a phase between SD and DS, but it would do nothing in this subspace. It's a decoherence-free subspace with respect to the difference operator. So to demonstrate this, we implemented, so we initialized our two ion qubits in the symmetric parity subspace. We initialized them in SS, turned on our transverse Ising Hamiltonian at a zero detuning, and looked at nice Rabi flops between SS and DD, where in contrast with the gate I've shown you before, where the tuning was small, and we did excite the antisymmetric spin state, you can see that the amplitude in the SD and DS states practically remains zero. Whereas if we initialize ourselves in the SD or DS states, we can see that we can flop between SD and DS, but the amplitude in SS and DD is zero. Now notice that if we now try to scan our transverse field across resonance, and we do that by scanning the tuning of our laser from the SD transition, the detuning of our two-photon transition is going to run twice as fast with respect to the Rabi resonance. And this would lead to a Heisenberg limited to a Rabi spectrum, which would be half as narrow. And the same is true in the antisymmetric subspace. So to see this, we now focus our laser beam on a single ion on a two-ion register, and we light shift either this right ion or this left ion. We scan the light shift by scanning the laser, the focused laser intensity. So we can scan the light shift up to from minus 400 hertz to plus 400 hertz. Plus and minus correspond to the right ion or the left ion being light shifted. And we also scan the tuning of our laser across resonance. And we measure how do we couple the two subspace. So we see that when we start out in the SD subspace, again, we don't couple population to the SS and DD subspace as we scan our laser parameters, but we see a nice Rabi resonance every time the difference in frequency between the two ions equals zero. Okay? And you see a nice clean resonance that is independent at all on the average tuning of the two lasers as we expected. It's a decoherence-free subspace with respect to this parameter. When we now initialize in the SS state, we see that when we're far detuned, so anyway, we see an average phase shift which is symmetric whether we shift the right ion or the left ion. So we see a nice symmetric shape around zero resonance. And we see a shift which is, it's not independent of the light shift, but we do see a shift every time we run over the resonance with our two-photon detuning. You can see here that this resonance is much noisier, and this is because we have much more noise in the average frequency of the laser with respect to our ion than in the difference in the frequency with respect to our ion. So to conclude this, and to verify that we have a Heisenberg limited spectroscopic signal, we now, in the symmetric subspace, scan very carefully around resonance and compare the width of the peak that we get with respect to the single ion peak, and we see that indeed we get a peak which is, to a very good approximation, a factor of two narrower. And we can do the same thing when scanning the gradient between the two ions in the antisymmetric subspace. So here we've shown Heisenberg limited Rabi spectroscopy on a two-ion crystal. Can you scale this up to a larger number of ions? Of course you can. You would need, however, higher weight operators that would couple S, 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 and so on to D, 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 and so on. So just putting in more ions and having a transverse Ising Hamiltonian for more ions would not do the work. In principle, these higher weight operators can be simulated using quantum simulators. We have a universal set of gates, so this is something we can do. It's more complicated. Again here, stability in the presence of classical noise is not guaranteed, similar to the Heisenberg, to the Ramsey approaches. Classical noise might create dephasing, which would completely render this approach useless, but it could still buy you a factor of a few. And if you want to see more details, Ravid Shaniv, who's attending the conference, is presenting a poster. So the next topic I wanted to discuss is a proposal. It's not an experiment, and this proposal deals with how to use entangled subspaces in order to mitigate systematic shifts in these transitions. So when you want to measure the absolute frequency of this transition, it's not enough to find with greater accuracy the frequency with which this transition happens in your lab. You have to evaluate whether different mechanisms shift this frequency from its desired ideal value. And what you see here is a table of the systematic shifts of a comparison of the two NIST aluminum plus ion clocks. And I'm not going to go over all these systematic shifts. What I'm going to say is that these shifts, grossly speaking, separate into two categories. One category is inertial errors. These are errors that come about due to the fact that your ion is not sitting in an inertial frame, and it's accelerating, or it feels gravity. And actually, ironically enough, these are the largest systematic shifts today, I think, or at least some of the largest systematic shifts in ion clocks, which is kind of funny because it means that the state-of-the-art clocks today are limited by the relativity of time itself. They're limited by the fact that there is no such thing as a universal time. And to mitigate these errors, I think there's not much you can do but to keep your ion as still as possible and to try and know your gravitational potential as well as possible. There's not much you can do. The other type of systematic shifts has to do with uncontrolled couplings of your clock states to the environment, magnetic fields, electric fields, and so on and so forth. Here, there's a lot you can do. One thing is you can try and decouple your ion from the environment. The other thing you can do is try to pick and choose transitions which have less susceptibility to changes in environmental parameters. So things, for example, which are first-order Zeeman insensitive, and so on and so forth. Probably the nastiest of all the shifts that come from this origin is due to black body radiation. And it's due to the fact that at room temperature apparatuses, the vacuum chamber emits black body radiation that corresponds to 300 Kelvin. And this radiation typically is sufficient to move most clocks, optical clocks, at 1 part in 10 to the 15, which is about 3 orders of magnitude larger than their absolute precision, which means that you've got to, in order for them to be precise at the 10 to minus 18 level, you need to be able to estimate the black body fields at 1 part per thousand, which is by no means an easy task. So let's look at two different typical trapped ion clocks and look at the shifts that they bring about. And when you choose different ions, you get different systematic shifts. Some of them are better, some of them are worse. So here we're looking at two optical quadrupole transitions, one in a calcium plus 40 ion, the other one is a ytterbium plus 174 ion. Both are considered as valid optical clocks. Both of them have some serious problems like being first-order Zeeman sensitive, and they both have electric quadrupole shifts, which are due to a gradient of the electric field across the atom. They also both have black body radiation shifts, which is due to the fact that there is a difference in the polarizability of the wave function of the ion of these two transitions. And you can see that the difference, the polarizabilities of these two clocks has roughly equal magnitude, but opposite sign. So how about the following idea? Instead of locking your laser to an atomic reference, which is the atomic reference of a single ion, we can lock it to an atomic reference, which is an entangled superposition of calcium plus and ytterbium plus. Now, this superposition is an interesting superposition. One thing to notice is that the frequency difference between these two superposition states, or the energy difference, corresponds to UV, to a UV wavelength. Even though in order to prepare or interrogate this superposition, you don't need UV light at all. All you need are the two clock lasers that act at the IR and visible laser, or two respective ions together. The other thing you can notice is that this superposition has no first-order Zeeman shift, because none of these states has any magnetic moment at all, to the extent that the magnetic moment of the electron here and the electron here match up, and they match up at the 10 to the minus 3 level. So there's no, at the 10 to the minus 3 level, there's no first-order Zeeman sensitivity. There is a sensitivity to a magnetic field gradient, as we've seen before. There's also a very small second-order Zeeman shift. Unlike other zero first-order Zeeman transitions that usually rely on hyperfine transitions, where the nuclear and the electron spins do not match at all, and a change in the magnetic field would introduce a first-order Zeeman effect. Here, a very large change in the magnetic field, which would change the fine structure coupling, would be needed in order to introduce a second-order Zeeman shift. So the second-order Zeeman shift here is very small. But I think the most important aspect of this superposition is that to the extent that the difference in polarizability match up, the black body radiation shift is at least a factor of 5 smaller, if not much more than that. And the relative shift of the black body radiation, because of the increase in wavelength, is an order of magnitude smaller at least. So here we've synthesized a trapped ion optical, an optical clock superposition, which mitigates many of the systematic shifts that the single ions would suffer from. And in fact, this idea is not limited to the example I've just shown. So I think that, in principle, instead of going to the periodic table and choose your optical clock of choice, in principle, what you could do is choose a combination of optical clocks, mix and match them in order to create superpositions. In principle, more than 2 ions can be involved, such that the different systematic shifts, the systematic shift of your will, would be significantly reduced. So if you like, you can open up another dimension to a periodic table with which you could choose your atomic clock reference. This is, again, a transparency in parentheses, and I just want to say that optical clock research is important not just for the sake of creating more and more stable and accurate frequency references, but also because you could use these things in order to search with the great precision with which we can measure these transitions. You can use it in order to measure very fundamental and subtle effects, and this is a proposal in a collaboration with Gilad Perez's group at the Weizmann Institute, which later grew to a much larger collaboration in which scalar Higgs-like forces will be able to detect or bound by using precision isotope shift measurements on optical clock transitions. How am I doing with time? 5 minutes, okay. So I don't have much time, so the third topic is going to be a topic I'm going to really rush along, and this is now does not deal with the optical clock transition. Here we're going to engineer superpositions of the electronic spin in the ground state, and we want to measure the magnetic interaction between 2 electrons. This is the Hamiltonian of dipole-dipole interactions, and the prefactor here goes down as 1 over d cubed with a magnetic moment of a single electronic spin, and the typical distances between ions in an ion trap, which are the micron scale, is a few millihertz large. So the way we measured this spin-spin coupling is by preparing superpositions in the antisymmetric subspace, the up-down and down-up subspace. In this subspace, the spin-spin Hamiltonian looks like a spin-exchange Hamiltonian, and the eigenstates are the singlet and the triplet states. At 2.4 micron, which is the smallest distance we could push our ions to, the coupling strength was 4 millihertz, which means that if we start out in the up-down state, the coupling between these two, the exchange interaction, would slowly rotate this state, this vector, around the singlet-triplet x-axis, and a spin excitation would slowly be exchanged from up down to down up, only it will take about 120 seconds for the excitation to be exchanged. So to measure this dynamics, you need long coherence times. Luckily, this decoherence-free subspace supplies you with exactly that. So by performing Ramsey spectroscopy in this decoherence-free subspace, we measured coherence times which extended to almost a minute, which is sufficiently long to measure spin-spin coupling. And these are the results of the experiment. By initializing the up-down state and waiting long enough, we could see a projection of this state on the XY plane. Again, by looking at parity oscillations, we could see an opposite phase fringe if we started the up-down state with respect to starting in the down-up state. By looking at these fringes, again, we could prove that the two spins have entangled themselves spontaneously with good statistical significance. And we could measure the spin-spin coupling as a function of distance and show that it indeed scales as 1 over d cubed. And in fact, I'm not going to give you details on that. By looking at the fundamental coupling between two electrons at these distances, we could also improve the limits on the existence of both pseudoscalar and axial vector fields, which are hypothesized to extend the standard model and explain riddles that we have, such as the weakness of CP violation and dark matter. And in particular, for the axial vector part, we're able to improve these bounds by 6 orders of magnitude. This was a collaboration with Derek Kimball from the University of California State. So this brings me to the summary. I've shown you how entangled or engineered subspaces can be used in order to perform or improve spectroscopy, both in the context of the resolution and the accuracy of optical atomic clocks, and both in order to measure the interaction between two electronic spins. I'm going to advertise a poster by Uti Ben Shlomi. I haven't touched at all about a whole other branch of activity we have in our group, which studies the interaction between a single trapped ion and a gas of ultra-cold neutral atoms. And there's a bunch of hardworking students working on this experiment as well, and Uti is presenting a poster on that. And with that, I'd like to thank all the ion trapping group, our funding agencies, and you for your attention.